Okay, so here we are talking about neutralization and the reactions that occur when an acid and a base react to make salt and water. However, the idea is very simple. Acids generate protons, bases generate hydroxides, and of course the combination of those make water. And that's the net ion reaction I talked about in class. Take out all the spectators, all the conjugate bases and acids that don't do anything in a strong acid, strong base scenario. This is the bottom line in neutralization. So, if I was to have potassium hydroxide, okay, KOH, which we know is a strong base, it's a group 1 ion in a hydroxide, which makes this soluble. So alkali metals and hydroxides and alkaline earth metals and hydroxides make strong bases because they're soluble. Okay, so this breaks apart into K plus and OH minus. As I talked about, the alkaline earth metals, which are group 2 elements, and the alkali metals are given their names from bases. Alkali and alkaline mean basic. So these guys, okay, because of their low charge density, they're big ions, they don't attract water very much, they can't pull H's off, are very soluble, okay, as you know from your solubility rules. All right, so they make soluble compounds, and very soluble compounds with the hydroxides means you're a strong base. It means you produce a lot of hydroxides because of your solubility. In any case, hydrochloric acid, as we learned, has a very large Ka. It dissociates just about completely, so we write it that way as well. And you add these together, of course what happens is, it's like a double replacement reaction. We have the positive ion and the negative ion switch places, and we make the salt, the potassium chloride, and we make the water. All we're doing is switching partners, as we've done in precipitation reactions. So neutralization reactions are really double replacement or metathesis reactions. But that's not really what this question's about. They're saying if I have 1.5 moles of hydrochloric acid, how many moles of KOH are needed? Well, I know that for every one H plus, every one hydrochloric acid, there is one proton or one H plus that comes off that. So this is really 1.5 moles of H pluses because of the strong or the high Ka, which means complete dissociation. If it's a strong acid, the moles of the molecule approximate very well the moles of the protons that come off. Okay, so I know at neutralization, because they said the word neutralize. Neutralize means, very important you understand this, where the protons equal the hydroxides from the chemicals. So how much base was needed to match all of the protons? Well, I know I have 1.5 moles of protons. So guess what? I need 1.5 moles of hydroxides. And because KOH is a strong base, there is 1.5 moles of hydroxides in 1.5 moles of KOH, because KOH completely dissolves. It's a very soluble salt with a hydroxide in it. So the answer, of course, is 1.5. Very simple. Okay, number 9. A little bit different because we have a little twist in this question. This is a diprotic acid. This acid has the ability to give off 2 protons. So we call this diprotic. Okay, what does that mean? That means that it can give off 2 H's. Okay, it's important to know that when you're doing these neutralization reactions. This sodium hydroxide is a strong base. It's a alkali metal with a hydroxide, but it's monoprotic. Monobasic we like to use. It gives off 1 hydroxide. So if I have 1.5 moles of H2SO3, okay, how many moles of the base do I need? Well, you can look at it and say, well, 1.5 moles of sulfuric acid, H2SO4, isn't that really 3 moles of protons? Absolutely. It's a strong acid, complete dissociation. Okay, although the second H that comes off would be helped by the action of the strong base. The first H comes off as strong. The second would come off for those that are looking at this little higher detail. But still, there's 3 moles of protons that can come off this. So really, 1.5 moles of this is really 3 moles of protons. So my friends, we would need, you've guessed it, 3 moles of hydroxide to neutralize that. And my friends in chemistry, we have NaOH. In NaOH, you only have 1 hydroxide per molecule, so you would need 3 moles of NaOH. Okay, now we could write this all out nice and neatly in a stoichiometry. Watch what I do here. 1.5 moles of H2SO4. Okay, and I know that for every 1 H2SO4, there is 2 protons. Right, it's diprotic. So I get rid of that. So I have moles of H pluses. Now, second thing I'm going to do. I know that for every H plus, 1 H plus, there is 1 hydroxide. And that's always. Neutralization, okay, is always this ratio. Oops. Always that ratio. Okay, so this ratio is always a constant. Okay. Now, next thing I'm going to do, this gets rid of my protons, and now I have moles of hydroxide. Notice the moles of hydroxide are twice. Okay, because it's 1.5 times 2. I'm crossing out the H, not the 2. Now, next thing, we have to evaluate our chemical here. Isn't there 1 hydroxide per 1 NaOH? And the answer is, of course there is. It's monobasic. So if you notice, everything cancels, and I would times that by 2, and I would get 3 moles of NaOH. Now you may say, Mr. Grodsky, why did you spend the time to do this part? Well, because we have chemicals that are dibasic. What if it was calcium hydroxide? Okay, and low enough quantities, because it's a strong base at low concentrations, but we'll consider it to be a strong base nonetheless. So what does this mean? If this was calcium hydroxide, there would be 2 hydroxides per every 1. And if you notice, we'd start up with what? 1.5. Now the answer is 3 moles, okay? But you can see that we've got to evaluate how many hydroxides are in the base, as we have to evaluate how many protons are in the acid when you do these types of problems. Okay? So that's all we have there. All right, so whether you do it by eyeballing it and seeing the ratio, or you do it by the stoic, like I did here, be my host. Now, what we're going to do now is move on to number 3. And these are called titration problems. Anytime we add a certain amount of an acid to neutralize a base, to find information about the other, we call that a volumetric titration. There's many types of titrations. They don't have to be acid and base. They could be gravimetric, where you're making it precipitate. They could be a redox titration, where you're titrating oxidizing agents with reducing agents. Bottom line is you're equaling one chemical with another somehow. You're normalizing it, and you're figuring out information about both. Case in point, I have a 0.4 molar base, and I have that volume of it. How much of this acid will neutralize it? Well, I'm going to do the stoichiometry first. Okay, and I'll show you another way to do it after. 0.40 molar is the strength of the base, but I'm going to start with the volume first. So 100 milliliters. I'm going to divide by 1,000 milliliters to get 1 liter. The milliliters go bye-bye. For every 1 liter, I have 0.4 moles, right? We did our stoichiometry with solutions. Liters go by. Now I got 4 moles of my KOH. I should have started with KOH over here. Okay, I'm not like in the blue, so let's change. Now I got moles of KOH. Well, for every 1 KOH, how many hydroxides? Because inevitably this is about matching hydroxides with protons. There is one, for every 1 KOH, there's 1 hydroxide. The KOH cancels. Now I've got moles of hydroxide. Great. Basically, I've taken my volume and times it by my moles. Okay. Now, next thing I'm going to do, I'm going to match my hydroxides. For every 1 hydroxide, there's one proton. That's neutralization, right? I'm matching the protons with the hydroxide. Now, my acid, I've got to evaluate that. For every 1H plus, isn't there 1 HCl? Okay, so a lot of canceling for easy numbers, isn't it? But we're just evaluating my base. If it was monobasic or dibasic, we're evaluating our acid. And here we're matching up the protons. This will always be the same. This could be a 2 to 1, 3 to 1. This could be a 2 to 1, 3 to 1 as well, but this one's always 1 to 1. So 100 divided by 1,000 is 0.1. 0.1 times 4 is 0.04. Okay, and times by 1 divided by 1. And that's basically what we have here in terms of, what did I solve for? I solved for moles. So I have 0.04 moles. They were looking for what volume, okay, and I found the moles, okay. So not exactly what we're asking for. So I found the moles of that, of the HCl, but I can now plug this in. A lot more work this way, but I'm evaluating it. So molarity is equal to 0.04 moles over the volume. I know the volume. Okay, so I'm trying to find the volume. That's my unknown, but I know that it's 0.8. Okay, so you can clearly see, to solve for this, you get a volume of 0.05 liters, which is equal to 50 milliliters. A lot of work, it seems like. I'm going to show you a nice, very simple way to do the same thing, but combine it into a nice little formula. Okay, so let's keep the stoich there. So we have MV of, let's say, the acid equals MV of the base. Okay, the acid's molarity is 0.8. The volume is our unknown. The molarity is 0.4. And the volume is 100 milliliters. Okay, solve for your unknown. Now, before we get into that, let's look carefully. Molarity times volume is equal to moles, right? Molarity times liter. If you look at molarity, molarity is equal to moles over liters. So when you multiply moles times liters, you get moles. So moles of the acid equals moles of the base. That's why this works. Sometimes they call this a titration formula, or they call this a motor vehicle formula or dilution formula, but you're matching. So if you do the formula, 0.4 times 100, okay, gives us what? 40 milliliters. You can divide that by 0.8, and that gives us 50 milliliters. Say, Mr. Grotsky, that was so much easier. Yes, but you have to be careful. We were evaluating how many hydroxides per chemical in this method. This method is easy to forget that. This acid is a 1-to-1. There's 1 H for every Cl, and there's 1 hydroxide for every. This is a 1-to-1, so we don't make any adjustments. We're going to have to make adjustments for the other ones down here, as I'm going to show you. So let's make sense of this. Does this make sense? Sure does. Doesn't it make sense that my volume is 50? If my acid is twice as strong as my base, the base is 0.4, the acid is 0.8. Doesn't it make sense that I need half as much of the base, or half as much of the acid as the base, right? I have 100 milliliters of 0.4 base, or hydroxides. To get the same number of moles, look at that equal sign, I need 50 milliliters if my acid is twice as strong. So this is the moles of H plus equal the moles of the OH minus. It's just an inverse relation between these two. If this number is halved, this one has to be doubled. Okay, so you could have circumvented this way or this way by just looking at the numbers in this case, but it's not always as simple. And if you don't do the stoichiometric method, the dimensional analysis method, you have to do it this way. Watch. So here's my MV of my acid. My acid is HNO3. I look at it, oh, monoprotic. MV of my base. No, it's NaOH. So this one's a 1-to-1. So same idea. I have 5 milliliters. Okay, I have 15. The molarity of my base is 2.0 molar. Okay, what's the molarity of my acid? And this is more of a realistic problem. I'm going to use the information about the base and how much base I need to neutralize a certain amount of acid by knowing that at some point the protons of the acid equal the hydroxides of the base. So 15 times 2 is 30, okay, and divide by 5, I get 6. So the answer is 6 molar. I just solved for my unknown. Now, does this make sense? Sure it does. If my acid is 3 times as concentrated as my base for the same volume, this has 3 times the amount of H pluses, then doesn't it make sense? I need 3 times more of this what? 3 times more of what? This volume to neutralize it. I need 3 times the amount of base in terms of volume to neutralize this acid because this acid is 3 times as strong. Look at that. So it makes a lot of sense. Okay, but you should know what we're really doing here is we're matching up what? The H pluses here equal the hydroxides here. That's how it works. Now this is a 1-to-1, so there's nothing for me to do here. Okay, but I evaluated that looking at this. Okay, let's move on. Now we have this acid. So interesting enough, as we go back, we are able to figure out the concentration of an acid that we don't know by neutralizing it with a base. As long as we know what the base's concentration is and how much volume it took and how much of the acid we're trying to neutralize, we can come up with the concentration of the other chemical. That's what a titration is. Use information about another. As long as you're matching something, you get information about the one you don't know. Okay, so here we go. I'm going to titrate, okay, hydrochloric acid with barium hydroxide. So I have my MV of my acid, HCl, and I have my MV of my base. All right. Now my base is barium hydroxide. Yes, you got it. That is dibasic. Okay, this is monoprotic. These are not equal. These are not equal yet. The moles of H pluses do not equal the moles of hydroxides because, all right, there is twice the number of hydroxides here. So we can't really do this. Now, I'm going to do this first, and then I'm going to evaluate the answer after. So here we go. I'm going to plug in the values. I have 0.25 molar of my acid. They're asking how much volume is needed to neutralize 20 milliliters, that's my volume, of a 0.10 molar base. Solve for V, so 20 times 0.1, okay, so a tenth, so you get 2, over 0.25. This gives us 8. So what we solve for? 8 milliliters. Okay, now, that was assuming this was a 1-to-1. So our answer, okay, is 8 if we assumed this was 1-to-1. But wait a minute, think with me for a second. There are twice the number of hydroxides. We're trying to figure out how much volume of this acid do I need to neutralize this base. Because there's really twice the number of hydroxides than I expected here, don't I need twice as much volume? 8 times 2, the answer would be 16 milliliters. So you can do this by doing it after and thinking it through, okay? Or, here's what you can do. You can actually write in, since this has 2 hydroxides, we're going to put that 2 right in the formula. Yep, I'm going to put it right here. We put it right here. So now, by dropping this 2 into the formula on the side that has more, watch what happens. By solving 0.2 times 2, okay, times 2, this gives me 4. 4 divided by 0.25 gives me 16. Okay, see how that worked? So when you do this, you can do it after like I did, or you can put the number of the multi-protic or multi-basic in this case right on the same side. And it'll give you the answer, which is 16. Or you can do it like I did. Let's go on and do another one. Okay, and I'll finish up with this one. I have, look at this, 2 to 1 here. So MV of the acid, my acid is H2SO4. It's 1.5 molar. The volume is what they're asking for, is equal to MV of the base. My base is NaOH. Okay, and I have 4.0 molar. That's my concentration. And my volume is 1.5 liters. Okay, and let's go find our V. And when we solve for this, we get V is equal to 4 times 0.15 divided by 1.5, just doing some simple algebra here. And you should get a 4 liters. So we started with liters. For those that didn't see what I did there, volume is going to be equal to 4 molar times 1.5 liters. Okay, and I'm just dividing by 1.5. And you can see that 1.5 disappears. Molarity cancels, you're left with liters, and of course you get 4 liters. Okay, that's assuming it's what? 1 to 1. It is not 1 to 1. There's twice as many what? Protons here. So what volume will I need to neutralize this base if I really have twice as much? For those that are thinking with me, you need half as much. So we come up with 4 liters, but the answer is really 2, because if this is diprotic, you have twice as much than you thought. So you'll need half as much to neutralize this base. So don't always think you're multiplying by 2. Now, if you don't like how I thought that through, watch what we also can do. Okay, I can also, just use that formula thing. There's 2 here. Put this 2 in the equation right here. So this goes right here. Let's solve for this again. Notice by solving for V, it's 4.0, and I'm going to divide by what? Also that 2, right? That goes to the other side. So you're dividing by 2, and that'll give you the 2 liters. I don't care how you do it. Okay? So that's what I'm going to go over. 13, please do for homework, but that's the end. Oh, I did make this too long. I feel so bad.